Welcome, roll up your sleeves. We got ourselves another engaging special topics talk on our hands here. This is Getting Your Hands Dirty with Statistics, aka Statistics by Hand. I'm Mark Williamson for the Biostatistics Core at the DaCCoTA project at the University of North Dakota. So for our goals of this talk is to run standard statistical tests by hand, unsurprisingly, since I monikered this stats by hand. So here's a quick run through of what we'll cover. First, we'll have a compacted history of statistics to provide the appropriate context for doing things by hand compared to the computer analysis that most people do for statistics all the time. Then we'll have a quick chart of tests that can be done by hand and then select the ones we'll actually do by hand. From there, we'll collect our own data in true by-hand fashion. Then we'll run a chi-square test, t-test, ANOVA, correlation, and finally regression, all by hand using the data we've collected. So before we move on to those actual slides, please take a moment to do the pre-test at the link here. Also, the link is found in the description below. So on to a brief history of statistics. Now, that is a topic that could have its own video itself, so this is very brief. I'm not going to go too much into it. I will rely on a couple other good summaries with references at 1 and 2 here. So anyways, to get into that, the 17th and 18th century was more theoretical, dealt with probability theory, inferential statistics, outlined preliminarily by Bernoulli and Bayes, with Bayes' theorem and various Bernoulli trials and processes. Then in the 19th century, statistics became increasingly applied to things like education, sociology, and then the hard sciences, especially biology, became pretty prevalent. The most notable statistician was Carl Friedrich Gauss, where we get the Gaussian or normal distribution. And then in the 20th century, we had things like regression, correlation, and then the advent of computer analysis. And big names here that really formed a lot of the tests we'll be doing today. Carl Pearson as the Pearson correlation, chi-squared. William Gossett, who is the inventor behind the student's t-test. The student is a nom de plume, as it were. And then Fisher, which dealt with ANOVA and maximum likelihood. So then let's zoom in a little bit more to the 20th century using this reference here. This history of statistics timeline. It had earlier centuries, but I'm just doing the 20th century. So early on, again, we see the names Pearson, Gossett, so student, and Fisher, and their contributions to the chi-squared, student's t-test, and ANOVA. Then later on in the 20th century, we start to see, if you're at all familiar with common statistical tests, Wilcoxon, Kruskal, Wallace, Spearman, these are all the last name of statisticians, and a lot of their tests, predominantly either non-parametric or appropriate multiple comparisons tests, they bear their name. So there's a Wilcoxon test named after Wilcoxon, Spearman based after Spearman, etc. But then at the very end, you start getting this computer technology. And again, it provided, of course, many advantages over calculation, made it a lot easier and simpler. In fact, you've probably, unless you've worked out some things in intro stats course, you've probably never done any of these intro tests by hand. And of course, a lot of modern statistical methods, like generalized linear mixed models as a prime example, cannot be done by hand, and they're exclusively by the computer. So the computer changed everything the way you did statistics, but leading up to it, statistics was done by hand, which is why this is an important idea, trying things out by hand, to really get into how statistics was done and is still done by the computer, but just under the hood. This will help illuminate it. So we're going to cut out our technology to really get our hands dirty, to understand statistics more, and kind of do this a little old school, sans technology. Next, let's take a look at what you can and cannot do by hand. Here's a swath of tests. I'm leaving non-parametric basic tests off to the side for now and just looking at parametric for t-test, ANOVA, etc. So for t-test, the three basic ones are 1 sample, 2 sample, and paired, and they all can resoundingly, yes, be done by hand. Absolutely, these are the simplest tests, so no problem. For frequency, both the Fisher's exact test, which is for smaller sample size, and chi-squared, yes, both can be done pretty easily. ANOVA, looking at 1-way, 2-way, and 3+ way ANOVA, so these are all going to be yes, 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 but start to question yourself if you really want to do a 3-way ANOVA by hand. Repeated and nest ANOVA as you can. I'm going to turn this into an orange. This is still a yes, but there's also the but why component in it. These are more complicated designs. Probably better to just let the computer do that. Turn our attention to regression correlation, Pearson correlation. Yes, of course. Simple linear regression, yes, of course. These are pretty straightforward. Multiple linear regression, this is getting into that yes, but why. So I'll put in an orange, yes, but why would you do that if you're starting to do multiple linear regression, especially model selection? You really want to turn to the computer. And for these last ones here, generalized linear models, linear mixed models, and generalized linear models, these are all going to be no. Pretty big no here. Especially, the linear and mixed models and generalized linear, no for sure. This is the generalized linear models, which includes things like logistic and Poisson regression. Some of them might conceivably be able to do by hand, but for all intents and purposes, no. So these are all no. All right, so for these assorted ones, these are more advanced, like multivariate analysis, Bayesian analysis, survival analysis, longitudinal analysis, etc. That is a great big nope dragon. Here we go. These are very advanced. Obviously, Bayesian analysis is on the simpler sort of Bayesian formula, sure, but like modern Bayesian analysis where you do Monte Carlo chains, all that stuff cannot be done by hand. So we kind of flesh this out. T-test, frequencies, and ANOVAs are all pretty easy to do by hand, and the simpler regression correlation, but then anything after that, really you're getting to the computer territory. So we've answered what you can do, but what will we do today? Well, we're going to sort of sample from all these areas. So for t-test, we'll do a 2-sample t-test. It's probably the most common. With frequencies, we'll check out the chi-squared. For ANOVA, we'll ease in our way with 1-way ANOVA. And then regression and correlation, we'll do both correlation and simple linear regression. Now, let's grow our data, shall we? So what I did to collect data is I looked at wood chips, because outside of the medical school, there's a variety of wood chips in sort of the plantings that I decided to collect and compare. So for the chi-square, I'm going to compare color, so either a light or a dark chip, across 2 different locations. Now, realistically, if you're doing sort of robust data analysis on this, you really should be using, with the number of samples I'll end up collecting, really should be using a Fisher's exact test for smaller sample sizes, because trying to do chi-squared with smaller samples can be problematic. But given that chi-squared I think is a little more generalizable or more common, I'm going to just use it, albeit slightly incorrectly, to give you the view of it. You can always just boost up the numbers if you want to do it more realistically. Anyways, enough on chi-square. For t-test, for these wood chips, I'll be looking at length across 2 locations. For ANOVA, we'll do length across 3 locations because ANOVA is essentially an extension of t-test. For correlation and regression, I'll be looking at length versus width. So that is what we plan to do. Next, let's look at our actual sections. So this was just after a snowfall, but I assure you there are wood chips here. You can, in section C right next to the building, you can see the wood chips near the sort of melty part of it, but there's wood chips in both section A and B. So then what I did, I collected 10 wood chips from each section. So 10 here, 10 here, 10 here. And then sorted them out in section A, B, and C, and then collected measurements from there. So for length and width, I just took a ruler. Because my ruler did not have centimeters very well, the measurement was off. I'm just going to use inches and round to the nearest increment. So width was measured like this at the widest part of it, and then length was to the full length, even if there was extensions. And that, along with our location as well as color, which I sort of did visually try to distinguish, that gives us this raw data here that I collected. From there, I translated it onto Excel spreadsheets, and this is just the reproduction here. You see with the length and width, I converted to decimals, so it's like, this is like 5.375 inches. Width is 0.5 inches. Color is either light or dark, and then location. So there is our homegrown data that we will use from now on. Jumping in here first with the chi-squared, here are our steps we'll proceed with. We'll state our hypothesis and select an alpha to test it against. Fill out a frequency table, then get observed and expected values, calculating subgroup values using that information. Then we'll calculate the test statistic, the chi-squared statistic. Then calculate degrees of freedom. Look up our calculated test statistics of a chi-squared table, and then state our conclusion of whether or not that test statistic was significant. So here's some more information here. This is going to be how we actually calculate our test statistics. It's the sum of the observed minus expected squared over expected. And so we'll get subgroups for each of these and then sum them all together. And the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Continuing on here, we'll tackle steps 1 through 6 here. Here's our actual data. We can see out of the total, 23 were light, only 7 were dark, and then it's spread across here. We see A and B pretty much have the same, mostly light, though C is approaching 50-50. So we're going to do 2 different chi-square tests. We're going to compare A to C and A to B. So looking at, for either of those tests, our null hypothesis is going to be there is no significant relationship between location and color. Well, the alternative is there is a significant relationship. That like one location has a significantly different ratio of light to dark than the other. That's essentially what's going on here for the alternative. Now alpha is going to be standard 0.05. So we can fill out our tables, frequency tables, and again this is just sort of taking this data here and throwing it in here, but we also want our column and row totals as well as overall total. This is kind of an easy way to show this, because we'll need that when we go to our observed and expected values. Observed values just take right from the table. We actually observed in section A 9 light and 1 dark, etc. But the expected are calculated from taking the row total minus the column total, so in this case 17 minus 10, divided by the total. And so we would have expected, if there's no difference, 8.5. Obviously, you can't have fractional amounts of wood chips, but this is statistic. This is sort of theoretical mathematical, so just ignore it. And so that's going to be 1.5 for the dark. And again, this is actually going to be symmetrical because you see that the 10 is the same here. So we're going to have the same down here. Then from there, what we can do is we can get the subgroup. I want to throw this down here, but I want to pop this up here. The subgroup is essentially this first thing here, and then for essentially the group light section A, and then that's the first summing, and then the second one is light dark in A, so forth. So we have 4 subgroups for each of these that we calculate by taking an observed, so 9 minus our expected 8.5, square it, divided by our expected 8.5, which gives us 0.0029. Do the same for the other ones, and we sum them all up together, and we'll display that to get our test statistics in the next slide. But before we do that, let's do the same sort of observed expected for our other comparison, A versus C. This first bit is going to be very similar. Just pop these numbers in here, get the expected. You can see that the shifts are a little bit different, but there's a symmetry here, so you can see that 8.5, 8.5, 7.5, 7.5, etc. Get the subgroups here. These are going to be a little bit larger because there really does seem to be more of a difference. But anyways, with that being said, so now moving on to actually calculating the test statistics. Again, we need to sum those subgroups. So for the chi-squared statistic, so this is for that A versus B, so I'm going to give a subset here. That was 0.029 from the last slide. And then we're going to times 2 because there's 2 of them, plus 0.167, again, times 2 because there's 2 of them. That equaled 0.39. So that's one test statistics for A and B. For A and C, it was 0.3 times 2 plus 0.9 times 2, which gives us 2.4. You see, this is much larger. The larger the test statistic, the more likely it is to be significant, more likely to be a real difference. We see that A and B we didn't really expect much of a difference because this was like off by only 1. This had 9, this had 8. But C was quite a bit different from A. It was almost at equal numbers, so unsurprisingly, this is much larger. Okay, but then what do we do with this? Well, first we need to get degrees of freedom, again, which is the number of rows and columns minus 1 multiplied by each other. So 2 minus 1, 2 minus 1, that all goes out to 1. So that's our degrees of freedom. Then what we can do with that is we can pull up a table, a frequency table. This is how you did it before the computer. You need to have your degrees of freedom over here and your alpha over here. This is getting a little bit in the way, so I'm going to just erase a few things and move it out. I don't think you need to see all of this. I'll just recreate the number. So that was 2.4. Okay. So on here, we need to get our correct alpha, which we had as 0.05. So we're going to have this column here, and then the degrees of freedom was 1. So the row is here, and then we just find this number here. So this is called the critical value, the critical test statistic. So that was, I'm just going to call that crit, 3.841. So essentially, if our calculated chi-square is larger than that, it is significant. If not, they're not significant. So neither of these is larger than 3.84. This one's not even close. It's about 10 times off, and this one's still quite a bit off. So what that means is there was, based on the chi-square, there's no significant difference between A and B, and no significant difference between A and C, given that our test statistics were smaller than the critical. So to state our conclusion definitively, there was no significant difference between A and B and A and C when it came to light and dark. However, remember, we should use Fisher's exact test for these sort of small sample sizes. in reality. And that can be done by hand too, but that's beyond what we're doing here. But one thing to sort of explore more about this by hand is, what would you have needed to have in your data to get a significant sample size or significant difference in our test statistics? Well, let's say, for example, that we don't have sections X or A and B. We have sections X and Y, where one has light and dark of 9,1, and Y has light dark of 1,9. Exact opposite. How would this pan out? Well, if we do the observed and expected, like we've seen, this gives us subgroups of 3.2 each, and if we sum all together, this is 12.8. So this is quite a bit larger than that 3.841. So something as drastic as this, even a chi-squared with too small of sample sizes could detect this. So there you go. Okay, we will turn our gaze to the ubiquitous t-test, so known as the student's t. The steps we will cover for this is state hypothesis and select alpha end tail. We'll sketch a graph out because we're starting to deal with numbers, numerical data along with categories. We'll calculate our group means, calculate our group sizes, and standard deviation for the groups. Use all this to calculate our test statistic, then get degrees of freedom, look up our test statistic in a table like we did before, and state our conclusion. And now here are equations for actually how to get things. So degrees of freedom is going to be our different ends of one group plus the end of the other group, and then minus 2. Our actual test statistic is going to be difference in means divided by things like standard deviation and our group sizes, squaring that. And to actually calculate standard deviation over here, there's a couple different formulas. It's whether if you have a population or a sample. This is for a population, but we're looking at just a sample, so we'll be using, I'll circle the correct standard deviation calculation that we need here. So there we go. Okay. So here are the first thing we'll cover. We'll state our hypothesis. This is our data we have for location A and B. So this is our grouping variable A, and we're comparing against B, and the numerical data is our length. So our hypothesis for this is going to be our mean of A, so mean length of A. The null is that it's equal to mean length of B. There's no difference between the length. Whereas the alternative is there is some difference. So then we can select our alpha, which is going to be 0.05, and then our tail. So that depends on whether you care about directionality or not. Two-tail doesn't test whether one is bigger than the other, it's whether they're different. You can do one tail, but two tails is standard, so we'll just do that there. And it's a little bit weaker, but more justifiable. Okay, and this is a graph I sort of sketched out the best I could by hand, because remember, before the advent of computers, even graphs had to be calculated by hand. Of course, they would probably had graph paper, and so they'd be a little more accurate than mine, but let's give us a general feel of it. That doesn't look like there's much difference between A and B. B might be slightly harder, but we'll see how our test pans out. Next, let's do some calculations here. Now, you could go as crazy as you want and do this all by hand, but for sort of clarity and time's sake, I did a lot of these in Excel spreadsheet for the sort of the minute, like summing and taking one value minus the other. So to get mean, we sum them up first, then get the number of samples and divide by that to get our means, 3.4 or 3.5 about, and then 3.9. So it looks like section B is a little larger, but let's see if that's significant. Next, to get our standard deviation, again, we have to take the actual values minus the mean. So that's what we have here, these two columns here, and then square that. So we did that, and then sum those all up. We get here, and then divide by n minus 1, so 9, so 10 minus 1, and then take the square root to get our standard deviation here. That was for group A, and then for group B, we did the same thing, and a little bit higher standard deviation here. Okay, then to get the test statistic, we're going to plug that all into this equation here. So again, we need to have the difference in mean. So I'm going to start using arrows. Okay, here, let's color here. So again, mean of A goes here, mean of B goes here, and then we have to take our standard deviation and square it. So throw that in there, throw this one in here, square it, and then divide by our number n. So 10 gives us minus negative 0.46 essentially, and then square root of that is 0.55. So we have this division that gives us negative 0.84. So that is the number of our t-test statistic, or t-value as it were. All right, let's calculate degrees of freedom. That is going to be fairly straightforward here. I'm going to take degrees of freedom is going to be 10. That's group 1 plus 10, group 2 minus 2. It's going to be 18. And again, our t-value that we're looking at is going to be negative 0.84. So let's look up our test statistics and the value. So since we had two tails, we go here, and then we want a t-value or a alpha value of 0.05. Then we added degrees of freedom of 18, so we're going to go down here. And that is going to give us a critical value of 2.101. So I'm going to make that bigger, 0.1. And comparing that, and this can be essentially plus or minus. And given that t is negative, that tells directionality, essentially 0, negative 0.84, that's a lot smaller than 2.10. Essentially, that means it is not significant. There is no significant difference between A and B. So the mean length of A was essentially equal. There's no evidence to suggest it was any different from B. Okay, but just like what we did with our chi-square, we can imagine, well, what would it mean to change our data to get a significant outcome? So what we're doing here, all test statistics is essentially a signal over noise divided by noise. So our signal here was the difference in our means, and then the noise was essentially had to do with standard deviation. So two ways to get a bigger t-value would be either to have a bigger signal, so you could boost the signal, or you can have a smaller amount of noise, reduce the noise. And so if we boosted our signal, so what if instead of A and B, with the differences very slight, what if B's mean length was 5 inches? Well, that would give a top value here of 1.5, negative 1.5. That would give us negative 2.73. So that is indeed bigger. So if you had 1.5 inches difference, that would be significant. Similar, if you reduce the noise, so made this number smaller. So what if there wasn't a lot of deviation? They're actually pretty tight. Dropping that out quite a bit, several fold, you could get something like negative 2.67, which again would be significant. So we can see here, part of this, if there maybe really was a real but slight difference between A and B, you could ameliorate this and detect this by collecting more and more samples, because the more and more samples you get, the more you can essentially reduce the error from the noise to actually detect what you are. Though I suspect what's going on here, there isn't a real difference, because they're just wood chips. They probably came from the same source. But if you had a more biologically or scientifically relevant case, more sample sizes would be helpful. That's why collecting as many samples as is reasonable is usually a good process. With that, let's take our dip into ANOVA, which is the logical extension of the t-test with more than 2 groups. So we're going to again state hypothesis and alpha, then we'll sketch a graph. calculate group means and overall mean, get these regression and error sums of squares and total, get some degrees of freedom, then mean squares of treatment and mean squares of error to be able to calculate our test statistic, the F statistic. Look up the statistic on the table, as you see is a common theme when you don't have the luxury of a computer, and then state our conclusion. So this is the formulas we'll be needing to deal with. This first row is how we get our degrees of freedom, how we get our sums of squares. So this is the model, that's the regression sums of squares, and then the error sums of squares, and then total, and mean squares. And then essentially the F statistics is, again, is that signal to noise sort of ratio. It's the mean squares of treatment divided by the mean squares of error. So to do that, go over looking at hypothesis and alpha. So again, we now have three groups, A, B, and C, and we're comparing length. And so our hypothesis is that the null is that they're all the same. There's no difference between them. And then the alternative, there's different ways to put this, but I kind of like to write out all the possibilities. That there's that, to say it in plain language, is at least one mean is different. But to sort of calculate that like we have here, we could either have A and B not being equal, or B and C not being equal, or none of them being equal to each other. Anyways, with that, our alpha is going to be standard 0.05, and our graph is going to be very similar to our t-test, except for we have a third category, C. Again, I'm not really, because of this graph, I'm expecting there's not going to be really a difference because they look pretty similar. C does have some higher ones, but those kind of look like outliers. Anyways, jumping into various calculations. Just a reminder here for our sums of squares what the equations are going to be. We're going to get our overall group means and overall mean by summing these up across the groups and divided by 10 and getting the group means here. And then of course doing that for all of them at once to get the overall mean. Because why we need these is for the regression sums of squares, you're going to take for each group its mean divided by the overall mean squared and then times the number of samples. And that is going to give us that for each of the groups, and we're going to sum that because there's a summation here to get our total. So this is our regression sums of squares. To get the error sums of squares, we're going to need to take the standard deviation and 1 minus the sample number. Get that all here. So these are them kind of raw, and then you're going to sum them all up. So for this, each of the groups A, B, and C, here's the sub error, and then total that all up to 52. That is the error sum of squares, and the total is just these two values plus each other. So this one plus this one equals the total sum of squares. Okay, moving, humming right along here, let's calculate our different degrees of freedom and mean square. So we already have our regression and error sums of squares and the total sums of squares. Now let's get degrees of freedom. So for treatment, that's just going to be the number of groups minus 1. So we have 3 groups, A, B, and C minus 1 equals 2. Circle here. For the error, it's going to be the total n. So we had 30 minus the number of groups, which is 3. So that's going to be 27. And for the total degrees of freedom, that was the total number minus 1, so that's going to be 29, but we won't really need this any later here. This is just for completeness. So to get the mean square, that's going to be the associated sum of square divided by their degrees of freedom to equal the mean square. So for treatment, that is going to be 1.86 divided by 2. It's going to be 0.93. Then for the error, that's 52.16 divided by 27, which is 1.93, and then to give our F statistics, so these aren't, ignore these. Anyways, to get the F statistic, we're just going to divide our treatment divided by our error, and that is going to give us, divide the two, show that here, 0.48. So our test statistic is 0.48. Keep that number in mind as we look up the statistic table and state our conclusion. So our degrees of freedom are going to be, for the first one, that's going to be our treatment. That's going to be 2. So we'll actually just circle this here. And for degrees of freedom 2 is our error, 27. You can see here that our critical F value is 3. So I'm going to go F crit. So again, we need to be larger than this, 3.541. And ours we actually calculated was quite a bit smaller, 0.48. So what that means in conclusion is there is no significant difference between groups A, B, and C. Again, if we really wanted to boost our signal or reduce our noise, because this F statistic is just like the T statistic, it's a signal to noise ratio. That's what a test statistic can be thought of. If we boost the signal by 10 times, the 10 times difference, we could get a significant F value, or if we reduce the noise by essentially 10 times much smaller noise, we could get that just sort of like we did with the t-test. But as it stands here with our small sample size and not really much difference between the wood chips, there was no significant ANOVA result. Now, if you were doing this by hand, you found a significant result, you would have to do post hoc tests to distinguish which ones were different. But that is best left for the computer anyways. Okay, then, we have shifted out of the realm of a numerical and categorical variable like t-test and ANOVA, or two categorical variables like the chi-squared, to only numerical variables with correlation and regression, where we have length compared against width. So the steps, like we've done before, state hypothesis, and now a tail again. We're going to sketch a graph, calculate the means of x and y, the difference between these other variables, get our correlation coefficient, also known as R, calculate degrees of freedom, look up the coefficients as always, and state our conclusion. So this is how we get our correlation coefficient, also known as the Pearson correlation coefficient by none other than Pearson. We're going to be getting these different summations across x and the mean of x, y and the mean of y for all the individuals, sum them up, and there's a square root of these various differences as well. So, to get into that, to do our hypothesis and tail, here's the data. We're looking at length versus width, and we're not caring about groups, so this is the first 20. So, the null is pretty basic, no significant correlation. There's no significant relationship between length and width. As one increases, the other doesn't do something like increase or decrease regularly. And H1 is there is a significant correlation. That how one changes will affect how another changes. Or there's a relationship between, not necessarily causation. We'll do a two-tailed test because, again, that's more standard. And I'll bet statistically weaker, but you need to sort of justify specifically if we do a one-tailed test, which we don't need to do here. And I sketched a graph with a little bit more graph liney lines to make it easier, but we can see that as length goes up and length goes up this way, width goes this way, that really doesn't look like to be any sort of relationship, but let's run the test anyways. So let's calculate the means of x and y. And again, just a reminder, this is our eventual correlation coefficient. Again, I turn to my good friend the spreadsheet. So here's our 20 samples, have their length and width, and we got the sum and then the mean. So let's pull out our handy dandy little highlighter again. And see here that the means down here, the means x and y is which we'll need for these later calculations, because we want to get these groups here, x minus the mean of x, y minus the mean of y. So we're doing each of these here, and then we also need to, eventually need to sum them. But we'll just do that right here where we take this whole upper one, so x minus the mean of x times y minus the mean of y for all the individuals, sum them all up, and that gives us the top subcategory here, so with this big variable. And then to get the bottom two, this one here and this one here, we're going to take that squared, sum them up, and have them down here. So that is what we're going to do here. We've got all the information we need. So let's actually calculate this. So let's switch over to drawing something, because I can do these numbers by hand without too much loss of time. So R, that is going to be the sum here. So that's going to be, I'm going to just round 0.39 divided by the square root of these two variables, 28 and 0.45, 28 point, and we'll round up to 6 times 0.45, which gives us, again, this is going to be that sort of signal to noise ratio, negative 0.39, take it like this, 3.57, and we're seeing that it's going to be negative 0.11. So very small, but to conclude what this is significant, we need our degrees of freedom first. We know that that's just going to be the total number of samples minus 2, so that's going to be 18. And so we look this up here. Again, we need our alpha value. That's going to be 0.05. Our degrees of freedom is 18. So we go here. We look at both rows. The critical R value is essentially 0.44. And ours was negative 0.11. See that this one is much bigger, so this was not significantly different. There was no significant correlation between length and width. So that is our. We will at last turn our gaze to regression, a close relative correlation. Now there is statistical tests for regression that are similar to, essentially have T and F test components built into it, but here for our purposes, we're just going to use regression to calculate a regression line. So a linear equation that best fits the relation between our length and our width. So to do that, we'll have our steps here of stating a hypothesis, sketching graph, calculating different variables, calculating the sums of the variables, and getting intercept and slope of our equation, filling out that equation, adding our line to our graph, and having some sort of conclusion here. So these are the equations that will be needed to get our intercept and slope, and now these are shown as called A and B, and that is how some people do it. However, I prefer to call them B0 and B1, so cross that out here, B0 and B1. You can see here that we're going to need summing up various y's, x's, x squareds, x times y, as well as the number of samples. So let's get to that portion of it. To do that, let's get our hypothesis and graph out of the way. Again, this is our data, length and width across 20 samples. We are expecting no significant relationship for a null hypothesis, so the line will essentially be not different from flat. A significant relationship would mean as x or y increased, or sorry, as y increased, x increased or decreased significantly, so the line will have some sort of real slope to it. And our graph is going to be unchanged from correlation because we're not showing anything different. I expect the line to be essentially flat, but we'll see. Okay, let's calculate some variables here. We will again use our lovely Excel to sort of speed things up. You could, of course, calculate this all tediously by hand, but hey, we have to have limits somewhere. So for our length and width, we just have that replicated here as well as their sums. X times y for all of them, summed, x squared and y squared, and so the sums are really what we're, that's black, we don't want black, we want green so we can still see. All right, so those are going to be the sums we'll be using in these equations for the slope and intercept. And to pull that out, as I've done here, we can see, for example, sum of y, that was 11.38, so I rounded up, here's that, times all these other ones. I'm not going to go into it, but you can see that they all match one of these sums here. You can take that all together, and unsurprisingly, we have yet again a sort of signal to noise ratio, one number divided by the other, give us our slope of 0.62, and an intercept of 0.062 and a slope of negative 0.01. So we can fill out our equation here. So y equals our intercept times plus slope times x. And so we can say our width is going to be 0.062 minus, because this was a minus, length times 0.001. So what that translates to, we actually add the line to the graph. Bleep. It's essentially not much different from a flat line. We can see that the intercept, which is here, is when x is 0, what y is. We see that as 0.62. And then the slope is, how this line changes, and we see that it changes very slightly negative actually, as length increases with slightly decreased. But it's so much not different from 0. We can just see that we state the conclusion that there's no significance. Again, we saw one way to show whether it was significant or not statistically was using that correlation, but there's also certain things with, again, R and F statistics involved you can do. It's a little easier. It's much easier on the computer, but this is sort of visually showing with the equation how insignificant they are. Well, we've been able to do several tests by hand, but let's compare and see how well our values we got by hand match up to the computer. So here, what we've gotten from our methods by hand. And let's go through each of them. With the chi-square, the computer spits out these variables. So essentially exactly on or within rounding to 2 digits. So not bad at all. T-test. Again, we're seeing a common theme. Rounded to 2 digits, they're exactly the same. Same one here. And again, if we round to 2 digits, same and same. So what we see is the computer is just doing the same thing we're doing underneath the hood of when you type in the code, like if you bloop a chi-squared, or you blip a chi-squared again, spit out a t-test, punch in ANOVA, or tippity-tip, tap-tap, type a correlation or regression. It's really doing what we did by hand underneath the hood, blazingly fast and to higher degrees of accuracy, as they don't round like we do at certain phases. But you get the same sort of result in a fraction of the time. But this helps show you that by hand, you can really do a lot of this stuff if you really had to. Another comparison, this is where computers are even better. I had those awful graphs. The wave of our hand, we can make much nicer box plots using this code, or of ANOVA, bigger box plots, and this, even better regression plots. So, we've come to the end of our time here. Some conclusions. I think undeniably, we can run classical statistical tests by hand, and it's possible, and well, I don't think it's fun, but it's certainly possible. And hopefully this helped you tease open the black box of taking your raw numbers, put it into a computer, and letting the computer output a couple numbers as a result. Hopefully this helped you get it under your nails as you did it by hand, as it were. And now, feel free. We didn't do everything you can do by hand. You can go crazy with more advanced examples. You can do multiple regression by hand if you have nothing to do on a weekend and don't particularly like having friends, but you can do it. Normally, though, for most things, once you've got the concepts down, you can just use a computer. Because again, a lot of the stuff I did here, I summarized relatively quickly, but it took me a couple hours, whereas you can punch it out on a computer for a couple minutes. So, before you go, it would really help if you took the post-test and survey to assess your knowledge. It can be found here in the links in the description below. Here are our references peppered across the talk. For more information, for getting the first-hand source of some of these test statistics, the tables that I used, etc. And finally, as always, the DaCCoTA is supported by the NIH under an award number. Please reference us if you found this useful. Thank you, and have a hearty day.